My mom was like me driving. When we were learning to drive, my mom got in the car one time and my oldest sister and my brother were going to be driving.
Alrighty, well, it's time to get started. So I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for your creation, this class, and we can study it. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. Let's see, so last time I was talking to you guys about relativity, special relativity, and what else? General relativity. And you may remember I mentioned Schwarzschild. I don't know if I can spell it or not. I'll try. This character. So Schwarzschild, he found the solution to general relativity for like a spherically symmetric problem. Like, say, you know, this would tell you how general relativity predicted gravity would behave, for instance, due to a planet which was like a sphere, or a star which was like a sphere. And it had interesting features. Of course, it reproduced Newtonian gravity in a certain sense, with a proper understanding. But it also suggested that there were things called black holes, that there actually was a structure where gravity was so strong that light couldn't even escape it. You know, I mentioned that it was interesting. His life got cut short. The reason it got cut short is he did all this apparently in trench warfare in World War I, which is like, what? So, I mean, that's impressive. I think you know you're in the middle of World War I and you managed to solve like the central problem in general relativity. And then he, I think, he caught like I forget if it's tuberculosis or one of these kind of sicknesses, and he passed about a year later. So I don't think he ever really saw the full appreciation of his work, but he was a pretty good theoretical physicist. So anyway, that was pretty much all I had to say about general relativity as a subject. You know, general relativity, it does have certain experimental. It does affect technology that you use. For example, GPS systems, they actually have to include they have to account for the time dilation that is from a general relativistic effect, because you know, as gravity changes, the time changes basically, and that has to be taken into account. Otherwise, the the GPS that you use would be off. So that's part of the calculation. So it's not just for, you know, esoteric things like black holes or stars or whatever. We all use GPS, and general relativity is part of that. The other thing, of course, is, like I said last time, general relativity explains, it predicts gravitational radiation, that there's things called gravity waves. We observe those with something called LIGO in about like 2010-ish or so. These giant lasers that are set up over long distances so you can see things wiggle basically. And so gravity waves are pretty hard to come by, but we have observed them, amazingly. And so that's one prediction of general relativity that you can work out. Another, of course, is the precession of the perihelion of Mercury, which is a complicated, basically the wobbling of the axis of Mercury can't be explained with just Newtonian gravity. So there are a few different little tidbits here and there that make us think that something about general relativity seems to be right. So that leads me to the story of cosmology. Do you guys know what cosmology is? That's cosmetology. Although, funny story, I went to a community college for electronics, and before my time, my professor, David, he liked to take the introverted, very introverted, very nerdy electronics students, and if they had to, he would make them give a talk on something, and like imagine you take physics, but oh, by the way, you have to give a talk on some current science topic. That's part of your physics course. Wouldn't that be fun? No? You guys don't do that, do you? Wait a minute, why don't I have a term paper in here?
No. I'll give a presentation.
Next.
I don't want term paper.
Next semester? Okay, yeah. Some of you will be in this course next semester though, right? You're like, no, there's other sections. I don't have to take yours, haha. Fair enough, but maybe it's closed, haha. No. Oh, wait a minute, nope. Silver lining, closer to graduation, it's a good thing. So, anyway, David would have them give their presentations on whatever science, or, he made them give like a 5-10 minute talk. Now, if you were giving a 5-minute talk, 10-minute talk to your fellow electronics students, of which there was maybe 10, that wouldn't be very imposing, right? So what does David do? Well, cosmetology, that's upstairs. So he would bring down all the lovely ladies for the audience. And then you'd have to give your talk to 20, females that you didn't know, who you were afraid of because you're an introverted electronics student. That's what he did to them. Yeah, I'm impressed with that. Now, he didn't do it to us. He didn't do it to me. But anyway, yeah.
Wondering if that was
No, I did not. My wife is not a hairdresser. Found her in physics graduate school. But anyway. So, let's see here. So cosmology is not that. So cosmology is study of the cosmos, right? So basically the study of the universe at large, all right? And so there's various ideas about this. Of course, what I think is that we have Genesis and we can read it and it tells us what happened, In the beginning, God created the heavens and the earth. That pretty much settles it for me. Like, he was there and he told us about it. We have a first-hand observer. Like, that's infinitely better than, what secular science tries to do about this issue. But I want to talk about some common ideas in science about cosmology, so we can talk about it together. So, first of all, I think a lot of the ancients probably said something, I think the Greeks said something along the lines like the universe had to always exist. That way, the universe doesn't have to explain what. If the universe has always existed, you don't have to explain why it exists, right? So that's convenient. So that's one of the reasons that ancient Greeks might have believed in an always existing universe. There are problems with that. One of the problems with that is what's known as Olber's paradox. Do you guys know about Olber's paradox? So if you have an infinite universe that's always existed, the problem is this. Starlight, light from stars, spreads out like a certain way. And when you study how the starlight spreads, and if you have an infinite universe, what you will find is that so much light is getting to you from the many, many stars which have always existed, which have existed a long time, that it gives you basically everything in the goodness gracious, everything in the sky would just be bright, essentially. So that's a problem because, of course, you look at the night sky and there's not a star everywhere, right? You see some light some places, but not everywhere. So it doesn't seem to comport with what Olber's paradox suggests. And then what do? You suggest, well, there's dust out there, right? So the dust is blocking the light, something like that. And there are various ideas that come forward to try to solve Olber's paradox. This led to, in the 19, let me try to give you a brief history of things here. So, goodness gracious, I should have got some tea. I don't remember dates. Where's this thing gone to? So there basically, I'm just gonna have to be approximate. Basically 1930, maybe 1930 to 1950-ish, something like that. You had the Big Bang Theory, although I think that name, Big Bang Theory, is from, the popular attribution of it seems to be from like 1948 or 1949. I think George Gamow was on some BBC program. He used this phrase and it just kind of took off. So that's the one the one thing, and then the other suggestion is this steady state theory. Now, the steady state theory was more like the ancient Greeks. It said that the universe has always existed, and it's infinite. It's always existing, and they had various mechanisms to try to overcome Olber's paradox. Big Bang theory people said that no, the universe started at an instant, at a cosmic singularity, and it expanded outward from there until where we are now, right? And they both assume a lot of the same basic features. I think they're both typically, I think you can find variations of either kind of theory. Like if we start talking about what are the possible cosmologies, we'd be here. Like you could do a whole undergraduate degree in that. There's just unending ideas about these things because they're very speculative. But they both assume a certain regularity of the universe, that the idea that we're really nowhere special in the universe, that if you look out, the universe looks the same in every different possible direction, right? That notion, isotropy, I believe it is. So what happened is this was, they argued back and forth. The steady state theory, I believe that Einstein was on the side of the steady state theory. The equations I showed you last time, Einstein's equations, they can be modified in such a way to, you can build a formula from Einstein's equations for the universe as a whole, like a bulk shape of the universe. There's a way to write down equations like that. And if you do that and you add something called the cosmological constant, so like Einstein, and originally added so-called cosmological constant. Sounds fancy, doesn't it? So the cosmological constant was a term basically inserted into Einstein's equations in the cosmological setting to try to make the universe have this steady state that just always existed, something like that. Now, what happened is that we observed things that more and more the observation seems to be on the side of the Big Bang theory as time went on. There were, for instance, a discovery of different things in the sky having different redshifts, right? So they, as you look out the sky, everything seemed to be redshift. So the way Doppler, you guys know about the Doppler effect? No.
Yeah.
So if you've ever been an ambulance drives past you, how it sounds different coming and going? Same thing happens with light. When things are going away from you, they get redshifted. That means that the frequency, the spectrum of the light gets shifted lower in frequency. It gets reddened. And so the light of different things is signature to the thing. It's called spectroscopy, right? The particular pattern of the light is almost like its DNA. Different stars, different things have particular signatures. So you can look at that and go, oh, well, that's that signature, but it's been shifted a little bit. You can see how much it's been redshifted. And so as we look out at the night sky and look at different objects, everything's redshifted. There's nothing that's there's very few things that are blue shifted. So that kind of says, well, things are going away from us, right? How does that happen? You could think about different things, right? Maybe we're the center of the universe and everything's just going away from us. That's a potential answer to that question, right? Not a popular one, but a possible potential one. But anyway, the answer ultimately given by the Big Bang theory is that space and time itself is expanding through something called that's the Big Bang theory. The space and time itself is expanding. And as it expands, the light that travels through the space gets stretched out as the universe gets stretched out, and that's called redshift. And then, so I think the Big Bang theory sort of killed the steady state theory in the minds of most scientists, probably with the discovery of the cosmic background. Well, there's different things that you can look to in the history that are supporting of it. Let me see if I can find some to tell you. Let's see here. So the big one, I suppose the big one was in 1965. So 1965, you had the cosmic background radiation. That's not the abbreviation. Is that the abbreviation? No, cosmic. Oh, I'm an idiot. Cosmic microwave, because that's where it was. Cosmic microwave background. So why would you be looking at microwaves? You're making popcorn? No, not that. So I think these are dudes that were just working on like communication systems. I don't believe that these two characters right here, Penzias and Wilson, I don't think these guys are even physicists, if I remember right. I believe these were just engineers who were setting up communication systems, and they had this, no matter which way they point their antenna, there's always this like white noise in the background everywhere at a particular frequency. And what they had discovered actually was the cosmic microwave background, which is a radiation which is everywhere in space of a particular frequency, and that's seen as evidence of the Big Bang Theory, because in the Big Bang Theory, you had that initially very hot, dense state. You all know the song. And, and then as it expanded, at a certain point, it cools, and radiation comes from that. And when that happened, I mean, basically a prediction of the Big Bang Theory is that there should be this cosmic microwave background everywhere, and that it should have kind of the properties that we see it does. So once they found that kind of, it became harder and harder to believe in the steady state theory, as some of the predictions of the Big Bang Theory seem to be borne out. Let me tell you a few things about the timeline for the Big Bang Theory. These are some fun things. So first of all, here's a fun one. How old is the universe according to Big Bang Theory? It's 13.787 plus or minus 0.02 billion. I love that they have stated the age with such certainty. They are certain of the age of the universe to plus or minus 0.02 billion years. That's pretty cool, that they're so certain of this. I don't believe them, and I'll tell you why as we go on here today. But this is the age which is estimated for the age of the universe based on various experimental things in the Big Bang Theory. Now, let me see if I can, in here I had some sampling from the Wikipedia article because it's got good stuff. Well, the Wikipedia article, if you read the totality of it, it's kind of like self-contradictory, because at the start of it, it says certain things aren't known for sure, but as you read on, it tells you for sure the details of the things which aren't known for sure, which is always interesting. But anyway, so here it goes. So you had the initial singularity. Let's see here. Let me just read, not write. The period from 10 to the minus 43rd seconds expansion, called the Planck epoch. Planck, I'll spell it eventually here. Capital P, it's a person, right? Like Max Planck, one of the founders of quantum mechanics. The Planck length, well, not Planck, well, the Planck length is 1.6 times 10 to the minus 35 meters, whatever that means. That's the Planck length. The temperature, consequently, let's see here. So at t equals to 10 to the minus, I'll get it eventually here, guys. At t equals minus 10 to the 43 seconds, the size of the universe was something like 10 to the minus 35 meters. Okay, great. Well, that's not true. We can't talk about the size of the universe. The universe is infinite, we think. We don't really know, right? All we know for sure is that it doesn't stop any which way we look in the sky, right? If it stopped right beyond where we can see, would we know? We wouldn't. So for sake of simplicity, we assume that the universe is infinite in these models. That is, of course, an assumption. Anyway, at this particular time, 10 to the minus 43, the the characteristic scale length of the universe was 10 to the minus 35 meter, and it consequently had a temperature of approximately 10 to the 32 degrees Celsius. Yowzers. That's kind of, that's a little toasty, isn't it? 10 to the 32 degrees Celsius. Yowzers. These are from the model, of course. And he says, the very concept of a particle breaks down in these conditions. Proper understanding of this period awaits the development of a theory of quantum gravity. We'll talk more about that as we go on in here, guys. Says that the Planck epoch was succeeded by the grand unification epoch beginning at 10 to the minus 43 seconds, where gravitation separated from the other forces as the universe temperature fell. So, all right. So at 10 to the minus 37 seconds, 10 to the minus 37 seconds, you had a phase transition. Do you guys know what a phase transition is?
Like water phases?
Yeah, like water. Exactly. So like when ice freezes, water changing to ice is an example of a phase transition, right? So where was I? I should have put a mark. Sorry, guys. Give me a second here. So this phase transition caused a cosmic inflation. Caused a cosmic inflation. All right. And what's that about? During which the universe grew exponentially. Unconstrained by light speed invariance, temperatures dropped by a factor of 100,000. This concept is well, I'll talk more about what motivates cosmic inflation. There's an experimental reason that we have to have inflation in Big Bang cosmology. Inflation, this cosmic inflation, was not originally part of Big Bang cosmology. Big Bang cosmology originally was like an initial hot dense state and then a uniform expansion from that singularity outward. Cosmic inflation is it's an add-on. It is a modification of the Big Bang cosmology. This is due to like Alan Guth and others. I just remember Alan Guth's name. Alan Guth, around 1980 or so, proposed inflationary cosmology. All right. When I was in graduate school, I asked my professor about inflationary cosmology, and he asked me, well, which one? He said there was like 150 of them. I can only assume the situation has gotten worse since then, because that was like 15 years ago, but there are literally hundreds of potential models of cosmic inflation. The point of cosmic inflation is that sometime in the very early universe, we go from we go through this exponential unfolding of the universe, basically from nothing to a very large extent in a very, very short time, like this here. Now, if you're like me, you might be bothered by the fact I'm talking about time. After all, I just got done telling you last class that time doesn't have meaning between different observers, so how is it I'm talking about time now? This is, after all, relativity. What gives? So the answer is we're talking about time with respect to that cosmic microwave background, the co-moving frame, as it's called. So there's an answer to that question. Anyway, so so different things happen in the inflation. Microscopic quantum fluctuation, so that occurred because of Heisenberg's uncertainty principle, were frozen in by inflation, becoming amplified into the seeds that would later become the large-scale structure of the universe. This is a quote from something. Around the time of 10 to the minus 36, around the time of 10 to the minus 36 seconds, we enter the electroweak epoch. So what's the electroweak epoch? Do you guys know? What's that talking about? And he says also when the strong nuclear force separates from the other forces. So you have, separation of the strong nuclear force. We'll talk more about those things maybe next time. or this time if I talk really fast, we'll see. All right, so then inflation stopped locally around 10 to the minus 33, around 10 to the minus 33 or 10 to the minus 32 seconds, inflation stops. Now you might say, why? Why does inflation stop? Why did it start? The answer, because we said so. All right, because it's needed in order to fit the data. No one has a concrete answer to where inflation comes from. Answers include dark energy, maybe something with like a Kaluza-Klein model, some sort of just unknown energy field that's everywhere, aliens. No, I don't know. I'm sure the aliens enter it here somewhere. I'll say more. Okay, so then around 10 to the minus 33 to 32 seconds, the universe's volume having increased by a factor. At this point, the universe's volume has increased, check this out, volume increased by factor of 10 to the 78. So we went from a scale, a scale length of like 10 to the minus 35 meters to a scale length of, what is that? What's 78 minus 35, what? 43. So now our scale length is something like 10 to the 43 meters at the end of inflation. So just to summarize what inflation says, consider this. What inflation's saying is it's saying that the universe was nothing, and then in an instant, it was huge. To me, this sounds like Genesis. Sorry. Like, it's now, of course, I do think we have to pay attention to the history in Genesis. I do think that the creation account is there for us for a reason. And I believe that inasmuch as these things contradict Genesis, that data will force us to the Genesis account in time. So there is, of course, disagreement about which came first, stars versus planets, all these kinds of things. But I think in time we'll be forced to the Genesis account. That's my belief. Now, anyway, I find it amusing that already experiment has forced us to the point of saying that there is a beginning to time. There is a beginning to the universe. And not just that, the initial creation event is much like we read in Genesis. It's not this slow, uniform, everything is as it always was. No, it's in an instant. It's created, But I say created. Now, at about 10 to the minus 12 seconds after the beginning of time, from the Big Bang clock here, the weak nuclear force separated is about 10 to the minus 12 seconds. After about 10 to the minus 11 seconds, the picture becomes less speculative. Okay, so everything up to 10 to the minus 11 seconds, according to Wikipedia, is completely speculative. And I would tend to agree. Anyway, so after 10 to the minus 11 seconds, at about 10 to the minus 6 seconds, we read quarks and gluons combine to form baryons, protons, and neutrons. So after about a microsecond, protons and neutrons are created, things that form ordinary matter, all right? And I should mention that also the other reason that people tend to believe the Big Bang Theory is something reasonable is it does suggest the abundances of helium and hydrogen that we see in the universe. Those are suggested by the Big Bang Theory, so that's kind of another feather in its cap. In any event, as the universe cooled, the rest energy density after about, so here's an interesting fun fact for you. After 379,000 years after the Big Bang, electrons and neutrons combined into atoms, mostly hydrogen, and were able to emit radiation. This relic radiation, which continues throughout the space largely unimpeded, is known as the CMB. So this right here is from about 379,000 years after the initial singularity of the Big Bang. It's frozen. Basically, it's like a flash of light. When light started to be able to be seen, that's what that is. Now, here's the problem. So that actually implies the inflation problem. And here's why. So we looked at the the pattern of the background radiation. And as you look at it in all directions, it's incredibly uniform, right? So the cosmic background radiation is incredibly uniform in all directions. Why is this a problem? Because it's a phase transition. Have you guys ever watched ice form? Have you ever seen ice form? What does it do? Does it just become all ice at once? Boop. You can see it. There's a phase parameter that it has to propagate at a certain speed. And you can see the ice forming. There's a communication of that ice formation signal that goes across the water. That's the phase transition. Phase transitions do not happen superluminally. They don't happen faster than the speed of light. So if the entire cosmic background radiation is all basically freezing out of the quark gluon plasma, the soup of particles before that, and it's all freezing out all at the same time, right? And it's freezing out in a homogeneity. Basically, the problem is it was so homogeneous, it suggested that that light was formed by a process which traveled faster than the speed of light at the time of its formation. That's a problem, because relativity says that c is the speed limit, so you can't have that. This forced the introduction of inflation. This is the so-called horizon problem. So the horizon problem forced the introduction of inflation. So the inflation fixes this because it says that no, like those patterns were expanded out from the original really small thing. It just expanded out really fast, and the rules don't apply during that inflation period, basically. So whoop, and then you've got the pattern. It's still uniform and smooth because it's from inflation. Hooray, haha. So we can ignore experiment that says that our theory is wrong, because we made up another untestable thing. Yay. But well, I don't know. Is it testable? Is it not? All right. So that, in a nutshell, is the Big Bang cosmology. And there's of course much more to tell you. The other thing I should mention is Hubble. Hubble's constant. Hubble basically said that the further you go away, the more the redshift. So you can tell how far something is by the redshift. And now the Hubble constant, it turns out, is not a constant. So that's fun. And there's much work that's been done over that in the last 100 years. And I think there's still quite a bit of debate as to actually what exactly the story is. I have a video we should watch. Let me show you guys. So this video, so something important has happened in the last about 5 years. There's something called the James Webb Space Telescope that was launched. So I have just a quick video that, yowzers, will inform us a little bit about the James Webb Space Telescope. I tried to find an interesting one that wasn't too long. I will play it at 1.5 speed because it's hilarious. 2 is too much. There we go, 1.5.
We discovered early galaxies that existed about 13 billion years ago, but researchers found that this galaxy is far more massive and mature than expected for a galaxy to be.
Right, let me just pause. So one of the big problems that has been found, essentially, is, so in this story of the universe being 13.8 billion years old, universes that you find that are like, say, 13 billion years old, they should look different than the galaxies now, rather. All right, they should have a different structure. And what basically they have found is that they have found galaxies that look more or less like the one that we're in right now, and they're only a couple 100 million years after the Big Bang. This is a big problem because it doesn't really fit into their standard story of stellar genesis. And this was predicted, actually. There's a creation scientist named Lyell. He predicted that as they look further out, they're going to find that the universe pretty much looks like it does here. And he also predicted that they would modify their theories to answer it such and so forth the way they have, which is kind of funny. But more about Lyell later. Let me go on here.
Well, it is not the first time that Webb has found such galaxies in the early universe. Ever since the Webb telescope began its journey, it has been challenging our standard cosmological theories. Well, the amazing telescope did not stop here. This time, this telescope has revealed a worrying thing about the universe. Recently, Nobel Prize-winning scientists revealed that the James Webb telescope has finally confirmed that our understanding of the universe was completely wrong. Well, it is not about big, like galaxies, but this time, some more important and new observations from the James Webb Telescope have shattered the age-old cosmological theories. Let's consider this. One of the pillars of cosmology is that the spatial distribution of matter in the universe is uniformly isotropic. It means that everything looks the same in all directions if you look over large enough distances. This is obvious, since the forces are expected to act equally throughout the universe on a large scale, and should therefore produce no observable inequalities in the large scale, structuring over the course of evolution of the matter field that was initially laid down by the Big Bang. Wherever you look, you will find the same density of matter, the same temperature, and the universe is expanding equally everywhere. For more than a century, scientists have been developing various cosmological models with the assumption that our universe is uniform in all directions. The Big Bang model, which is the best theory to understand the universe, is also based on this assumption. The cosmic microwave background radiation also shows that the universe is the same everywhere. But a recent study published February 6th in the Astrophysical Journal letter suggests that there may be something seriously wrong with this assumption. Recently, astronomers have confirmed that the expansion rate of our universe is not the same everywhere in the universe. In this paper, they revealed that depending on where we look, the universe is expanding at different rates. Well, this is a big problem now because if the universe is expanding at different rates in different places, then it will create a major problem for astronomers. This new study also suggests that we may be completely wrong about the current estimated age and nature of our universe. David Gross, a Nobel Prize-winning astronomer, said, "We wouldn't call it a tension or problem, but rather a crisis." Let's delve deeper into this discovery and learn how the new Webb telescope discovery confirms a crisis in cosmology. In 1929, Edwin Hubble provided the first observational evidence that our universe is expanding everywhere. Using the largest telescope of the time, he discovered that the more distant a galaxy is from us, the faster it appears to be receding into space. This means that the universe is expanding uniformly in all directions. From this discovery, scientists thought that if the universe is expanding, then this expansion must have started at some time in the past, which means that the universe must have a finite age. And since the expansion is occurring equally everywhere, by accurately determining the expansion rate called the Hubble constant, the cosmic clock can be rewound and the age of the universe calculated. But before the Hubble telescope was launched, there was a huge uncertainty over the expansion rate of the universe, or Hubble constant. This value is needed to calculate the age of the universe, estimate its evolution over billions of years, and understand the forces driving it. When the Hubble Space Telescope was launched, it revealed that the universe could be as young as 9.7 billion years or as old as 19.5 billion years. But this younger value presented a huge problem. It would mean the universe was younger than the oldest known stars. Over the centuries, astronomers have adopted many methods to measure the exact value of the expansion rate. But surprisingly, each method has produced different values. It's as if the universe is expanding differently for different observations. Currently, there are two gold standard methods for figuring out the Hubble constant. The first involves poring over tiny fluctuations in the cosmic microwave background, an ancient relic of the universe's first light produced just 380,000 years after the Big Bang. Between 2000
I was 1,000 years off.
astronomers mapped out this microwave fuzz using the European Space Agency's Planck satellite to infer a Hubble constant of roughly 67 kilometers per second per megaparsec. In the second method, we use a Cepheid variable star or supernova as the distance source. As Cepheids get brighter, they pulsate more slowly, giving astronomers a means to measure their absolute brightness. By comparing this brightness to their observed brightness, we can calculate how fast the universe is expanding. But this is where the mystery begins. According to Cepheid variable measurements, the universe's expansion rate is around 74 kilometers per second per megaparsec, an impossibly high value when compared to Planck's measurements. Initially, some scientists thought that the disparity could be a result of a measurement error. But recently, Adam Rees, professor of physics and astronomy at Johns Hopkins University, said, "We've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence." Also, the new images of James Webb Telescope confirm that the previous measurements are correct, and the universe is expanding differently in different places. This dispensary in the value of the expansion rate of the universe suggests that perhaps the universe is not the same everywhere. Well, if this is true, then our standard cosmological model would fall apart, since we cannot estimate the age and size of our universe with different values of expansion rate. And the most important question that will arise is, what is the reason for the universe expanding differently at different places? One intriguing reason could be that dark energy, the mysterious force that seems to be driving acceleration of the expansion of the universe, is itself not uniform. In other words, dark energy is stronger in some parts of the universe than others, causing different expansion rates. Scientists claim that if the universe is not homogeneous and isotropic, then it would mean that the physical laws as we understand them are impossible to comprehend. Just over the cosmological horizon, the force of gravity might act in reverse. The speed of light might be slower than walking speed, and unicorns could be real. This discovery of the Webb telescope has caused a great debate among astronomers. This is because we
Threw in unicorns.
the universe challenges
All right. I'm going to stop it here.
astronomers.
Excuse me. All right, yes. So let me close this out here. So you can watch much more lengthy ones from PBS or whatever that have, you know, far more blathering. But the other thing to talk about here, well, as I've watched a lot of videos on the James Webb Space Telescope, and that one kind of underemphasizes the severity of the early galaxies and what they mean for the standard story. Now, I think at the moment they're kind of, this tends to happen, you know, you find something which contradicts the given storyline, and then people kind of coalesce around a new explanation and never really explain to the public. They completely change their explanation for things. This is kind of the MO of cosmology and astrophysics. I really don't like the way they communicate what they know to the public, because what they know is incredibly speculative. And the other thing is, they have actually found things, if I understand correctly, they've found things where you can see things that are like they have a higher redshift in front of things with a lower redshift. Do you see the problem there? Like, you're seeing something that's further away in front of something that's closer. How's that work? So, like, it seems like maybe there's some hiccups in our understanding of how redshift works, and they may be more serious than we realize at the moment. I kind of expect that the next 30 years or so in cosmology are going to be a time of incredible upheaval. So right now they've only found these distant galaxies that are a couple 100 million years old. What happens when they find a distant galaxy which has got a redshift suggesting that it's like 14 billion years old? What happens when you find a galaxy which is older than the universe? You know, that could be a problem. So, like, galaxies exist inside the universe. By the way, the other thing to talk about that I haven't talked about yet today is this cosmic inflation tends to be bundled with the concept of a multiverse. So I read a book by Leonard Susskind. He says he's the father of string theory. That's kind of true, I guess. Anyway, he actually doesn't call it the multiverse. He calls it the megaverse, and it's a very interesting book. His start of the book, he basically has like this disclaimer: creationists and creation scientists and that kind of person are going to misuse my book and say that I'm really giving arguments that suggest that the universe is an incredibly special place that's been designed to have exactly the features that it does. But that's not what these arguments mean. Although it is what the arguments mean, actually. So much so that he is led to posit the existence of a plethora, a multitude of other universes. Why? Just to explain away the specialness of this universe. You see, this universe isn't so special if it's just one of a kabillion universes. It just happens to be the way that it is, where life is suitable, where the laws of physics we can understand. The mystery of the laws of physics being understandable is a mystery which weighed on Einstein. It's weighed on physicists who've understood how incredibly special it is that you know, beings ostensibly created by random chance and so forth somehow can understand the universe in the way we do. It doesn't make sense. Now, anyway, all this said, there are problems, of course, for the creation side of things. The most significant one of them, I would say, the one that probably troubles me the most, is the Starlight and Time problem, right? So if you believe the universe is 6,000 years old, how is it that we can see stars that are millions of light years away? The problem kind of explains itself, right? But I think that there's a variety of different answers. This is a helpful article that gives, like, I think probably some of the best answers that have been come up with. One of the ones is that the light was created in transit. I don't like this. I don't like that one at all. That one to me just seems nonsense. I used to like this one a lot. I still like it a lot. This is the speed of light is variable. Barry Setterfield was an Australian physicist who suggested that the speed of light was much faster at the creation event, and it's been exponentially decaying since then. That would allow for light from very, very far away things to get here faster. I'm actually an advocate for part 3. I think that the light, we can see it because that's part of how God created the universe. Like, he literally created the cosmos, he created everything, like it tells us about in Genesis. And in that process, he created the light. He already put it here. You can't understand it in terms of like traveling of light or anything like that. Those questions don't even make sense. It's actually how the universe was created for us to see the stars. So I think that, because I think ultimately the contradictions come from trying to impose a uniformitarian assumption that things are as they are right now and they always have been, and that's the error. There are other answers. Lyell, no, that's not Lyell. Is this Lyell? Lyell has this asynchronous light convention. He believes that the light travels one way. Lyell's got a weird explanation in my view. Starlight and Time is a book written by Russell Humphreys. He says that the universe is something like a white hole. A white hole is a time-reversed black hole, which allows for you to have 6 literal days on the Earth frame and billions of years other places. So that would solve certain problems, obviously, but it creates other problems which haven't been answered. I don't really know much about Josh Hartnett's explanation, but you can read about it if you want. I have a link to this in the announcements, yeah? And oh, this is the Lyell's. I forget what he calls it. The anisotropic. He's got a quick name for it. Anyway, yeah, he says basically light travels one way. Light travels different when it goes different ways, roughly speaking. That's probably not exactly what he's saying, but I don't care for it, to be honest. Anyway, so here's an article that has, I think, some of the most promising explanations. I really think I've come to believe what my community college friend Dale was an older fellow. He's about 40 when I was 20, and he come back to study electronics because it turns out that electronics knowledge kind of it ages. It becomes, so he had to come back to school. But Dale used to always say that if God could create a fully formed man, why he couldn't create a fully formed universe? And at the time I thought, well, that's not a really good explanation. But as time has gone on, I've realized that there's a lot of wisdom in that explanation, actually. And if you think about other things in creation, like, were the trees in the garden, when did they grow? They were grown, right? I'm pretty sure they were grown. You don't get the sense that they're like little saplings that just were created, right? Like, God created things, created a fully formed man, right? Did Adam have a belly button? Sorry, now I'm just messing around. All right, so let me give you guys back your test. Let me turn this thing off. So next time we will talk about the 4 forces in string theory. Woohoo!